Alright, I had a request for more videos in class. I think it was more so when kids are confused in class, they can have the excuse of, but I watched the video. But that's okay. We got another video, and it's all about electrolysis. So we know from looking at galvanic cells that certain chemical reactions can create electricity. That's when our E cell is positive and we have this galvanic cell, electrons run across the wire. But what if I have a reaction that's not thermodynamically favorable, or we have a negative E cell? Well, could I put in electricity, put in energy to make this reaction happen that wouldn't necessarily happen on its own? And the answer is yes, and it's called electrolysis. So I kind of gave away the definition, but what electrolysis is if I force a current, so I'm pulling electrons through the wire, electrons that don't want to go through the wire on their own, we can force that current and get a reaction that's not thermodynamically favorable to happen. So why would we want to do this? Well, if I have a dead battery, I might want to charge that battery. Creating aluminum metal, we use aluminum every day. The production of aluminum uses electrolysis. Making jewelry or silverware, so getting that nice shiny silver coating, but not pure silver, so a little cheaper option. And sometimes we want to split compounds into its parts. So here's a little side-by-side comparing and contrasting electrolytic cells and galvanic cells. So both electrolytic and galvanic cells, we will see reduction happening at the cathode. We'll see oxidation at the anode. We will have different charges, so to speak. Cathodes are thought of as negative, anodes positive in electrolytic. The opposite for galvanic. I'm going to be honest, it doesn't really impact us because we never talked about cathodes being positive, anodes being negative for galvanic, because it doesn't really have much impact on us in chemistry. You'll see that more in engineering and things like that. For electrolytic cell, anodes and cathodes are going to be in the same compartment, so like the same beaker. You saw with the demo that a galvanic cell, we have two separate compartments. The anode and the cathode are in two separate beakers, two separate containers. For an electrolytic cell to work, you need a battery. That's your source of energy, whereas a galvanic cell can be thought of as a battery because it's creating that electric current. All right. So one of the uses of electrolysis is splitting a compound like sodium chloride or table salt into its atoms. So here's sodium chloride, and I broke it apart into Na and Cl2. Why did I break Cl2 into a diatomic instead of just regular chlorine? Well, there are 7 elements that always are paired up or in the form of a diatomic. So the way I remember these 7 is the phrase hike bro, need Cliff Bar, right? So we got H for hike, there's our bro, need, and then the word cliff, and then I added bar because I'm not trying to climb any cliffs, but I'll eat a Cliff Bar if I'm hiking. That sounds nice. Okay, so I have my sodium chloride. Don't worry about balancing. You just really are taking the compound, splitting it into its elements, and checking to make sure that if you have a diatomic, you add a little 2. And then I assigned oxidation number. So alkali metals are always going to be that +1, so that means chlorine had to be -1, and anything in its standard state by itself is going to be 0, an element by itself. So there's our oxidation numbers. All right, so let's see what's happening here. Well, I see sodium is going from a +1 oxidation state to 0, so it's gaining electrons, which means we want it to be reduced in this reaction, and chlorine is losing electrons from -1 to 0, so it's going to be oxidized. The important thing about this is if we calculated E cell for this, so we found the half reaction for the reduction of sodium, we found the half reaction for the oxidation of chlorine, we would get a negative E cell value. This is not thermodynamically favorable. This does not happen on its own, and that's good for us. I don't think it would be a nice experience if I opened up my kitchen cabinet and the salt in there suddenly had decomposed into sodium, metal, and chlorine. Sodium is very aggressively reactive with water. Chlorine gas, not ideal to breathe in. So luckily for us, this is not thermodynamically favorable. This does not happen on its own. We can get this to happen, though. We can force it to happen if we add electrical energy from a battery. It'll force this non-spontaneous or this not thermodynamically favorable reaction to happen. So we can get it to happen by adding a battery. So I drew a nice little battery. It's got our wires coming out in our positive and our negative end. If we add this battery, that positive side of the battery, what it's going to do is it's going to pull electrons in, and it's pulling those electrons from chlorine which will oxidize the chlorine, right? Taking the electrons from chlorine. And the negative side of the battery is responsible for pushing the electrons out. So it's going to push electrons to the sodium, which will reduce the sodium. So here's a cute little picture side by side. On the left, we have a galvanic cell. You can see we have our anode, we have our cathode. The electrons go on the wire. You could put a voltmeter here to measure how much or what current, measure the current of the electrons, or in this case they put a light bulb, so proving that we're actually getting like a battery to light the light bulb. An electrolytic cell, we notice that the charges are flipped. Cool, don't really care that much if I'm being totally honest, but we still have the anode cathode. Electrons still go from anode to cathode, but we need a battery or some sort of electrical source, so this one's plugged into an outlet. The way this works though, notice we have a divide here. It's all one solution and it's actually molten sodium chloride, so we got to get salt hot enough to actually melt in the electrolytic cell. As you know, I tried to explain galvanic cells and no one knew what I was talking about, so I have a little obsession with this Tyler DeWitt guy because he explains galvanic cells and electrolytic cells way better than I do. So I suggest at this point, pause the video, open another tab. I want you, this is like a 30-minute video. I realize that's kind of aggressive. I just want you to watch 5 minutes of it where he explains how the electrolytic cell works, and he does all the cute stuff with the little ions and the electrons and flipping them over. Like, you'll love it, I promise. It's worth the 5 minutes. So please pause, watch that video, and then we'll join back together for some calculations. No, really, go watch the video. I'm not joking. It'll help you understand it. I didn't even try to explain it because he does it way better. Okay, hopefully you actually watched the video. So we have this kind of law, so to speak, that we're going to use, and this will help us do some stoichiometry with stoichiometry. I put that in air quotes. I know you can't see my hands, but some stoichiometry, so to speak, or conversions with for electrolysis. So Faraday's law says that the amount of substance being oxidized or reduced at each electrode during electrolysis is proportional to the amount of electricity that passes through. I'm like, to me, that's kind of like a duh, but I guess at the time this was very important. Maybe I don't understand enough to think of this as super monumental, but it makes sense to me. Okay, so here are the steps for doing stoichiometry. Really, it's just unit conversion, honestly, where we're switching from one unit to the other of electrolytic processes. I'm going to walk through each step one at a time, so I'm not going to read these to you because I'm going to go through each one in depth. Okay, one of the first steps is that we're going to convert the current and time to a quantity of charge in coulombs. So typically these problems, they're going to tell you that they're applying a certain amount of amps or amperes. So we need to convert that into a unit that we can actually see. And so what you need to know is that 1 amp is equal to 1 coulomb per second. Volts is also a way to measure current. We saw 1 volt is 1 joule per coulomb. Great, just different scales. So depending on what they give you for the problem. We used this guy more when we were doing our giraffe equation, delta G equals negative NFE, just so that we could get delta G in joules. Cool. We're probably going to use this one more for electrolysis. Next, we're going to convert that charge in coulombs, because we have coulombs per second. We're going to turn that into moles of electrons. And we know Faraday's constant is 96,485, and the unit is coulombs per mole of electrons, 1 mole of electrons. So if I split that unit, anytime you have a unit that's something per something else, really we're saying if I have 1 mole of electrons, that's equal to 96,485 coulombs. So all I'm doing is splitting a Faraday's constant into 2 sides of this equality for conversion purposes. Once we have moles of electrons, we can figure out how many moles of whatever, usually metal, we're looking for. So we look at the balanced redox reaction, and so if we have a certain number of moles of reactions from the calculation so far, we're going to look at the number of moles transferred in the redox. That was N in our delta G equals negative NFE equation, and then to however many moles of the substance, which is usually 1 mole of the substance that we're making. And then we're just going to take a little trip to Mole Island. Using molar mass, we'll go from moles to grams. Alright, I'm going to walk you slowly through this one. This is a typical practice problem, and then I have a couple more for you to try that I'll let you try, and then I'll kind of put up the answers and have you check. But this one we'll go through together. So it says, how long must a current of 5 amperes, or A, be applied to a solution of Ag plus to produce 10.5 grams of silver? So our first step is to write the half reaction showing what is actually happening. So if I have a solution of Ag+, it needs to gain 1 electron to form solid silver. Okay, so there's my half reaction. And the problem gave us some other useful information, and then there's some things we just know, some things that would be on your formula sheet for on the AP exam. So if I have a current of 5 amperes, we know now that 5 amperes is equal to 5 coulombs per second. So what I did is I split that in green. 5 coulombs equals 1 second. That'll be useful for us. And then we also know Faraday's constant, 96,485 coulombs per mole of electrons. So I split that into 96,400, 85. That should be a 5 right there, just go with it, is equal to 1 mole of electrons. So this one we're kind of working through those steps I gave you backwards. So they tell me how much silver I want to produce. We're trying to end with time, with seconds. So I'm going to take the 10.5 grams of silver, and I'm going to use the molar mass of silver, 107.87 grams per mole, and then 1 mole on top. So when I multiply this fraction, grams of silver will cancel, and I'm left with moles of silver. So I took that answer, and for every, so we got 0.0973 moles of silver. Well, for every 1 mole of silver, we can just leave that, 1 mole of silver, we need 1 mole of electrons. So now I have moles of electrons. Moles of silver is gone, and we're left with electrons. So now that I have moles of electrons, I'm going to use Faraday's constant, and so if you look at this red here, I have it as an equality, so I can decide what one part's going to go on top, one part's going to go on bottom of this fraction, and I want the units to cancel. So I'm going to put the 96,485 coulombs on top and 1 mole of electrons on bottom, because I don't actually have 1 mole of electrons, I only have 0.0973 moles of electrons. So moles of electron will cancel when I multiply by this fraction, and now I have 9,391.8 coulombs. So last step is we're going to use the current that was given, that it was 5 amps or 5 coulombs per second. So 5 coulombs is equal to 1 second. So again, I get to decide what goes on top and bottom, so units cancel. Well, I want the coulombs to cancel, so I put 5 coulombs on the bottom, 1 second on top. Coulombs cancel, and I multiply by this fraction, and I'm left with 1,878 seconds. 1,878 seconds honestly means absolutely nothing to me, so I know there's 60 seconds in 1 minute, so I just divide that guy by 60, or 1 over 60, and I get, or multiply by the fraction 1 over 60, I should say, and I get 31.3 minutes. So what this tells me, this is my final answer, it takes 31.3 minutes with a current of 5 amps to this solution. So if I run 5 amps through this solution of Ag+, I will make, after 31.3 minutes, 10.5 grams of silver. Alright, I want you to try this one, and then I'm going to put the answer up. But here's what it says. How long will it take to plate out each of the following with a current of 100 amps? And it's 1 kilogram of aluminum from an aqueous Al3+. This may be one on your problem set. I think maybe not 77A. I think I asked you to do a different letter, potentially. So this should help you figure out how to do one on your problem set. Okay. This might look intimidating. I think you guys can handle it, but what I did is I squished all of these conversions together. So when I multiplied 1,000 across the top, and then I divided by all the numbers on the bottom, multiplied. Or you could do each individually, right? Get the answer from the first multiplication, use it for the second, like I did on the one I walked through. But you should see that all of our units eventually cancel. And so I'll kind of walk you through what each thing means here if you need that extra help. Especially if your answer was wrong. So I started with my equation, so I have Al3+, that's my aqueous. It takes 3 electrons to make Al solid, right, to get that neutral. I know that if we have 1 kilogram of aluminum, there's 1,000 grams in a kilogram, so I just started in grams right here. I didn't show that conversion, I just know 1 kilogram is 1,000 grams. So that's what we're starting with. So my first step was to get moles of aluminum, so I used the molar mass of aluminum here. And so what happens is my grams of aluminum cancels, and so now if we stopped, we'd be in moles of aluminum. Now I'm going to look at the reaction. Well, for every 1 mole of aluminum, I need 3 moles of electrons. So that's here, 1 mole of aluminum is 3 moles of electrons, so my moles of aluminum cancel. Again, if we stopped here, our answer would be in moles of electrons. Now I'm going to use Faraday's constant, which is 96,485 coulombs per 1 mole. I put 1 mole on the bottom for this problem because I want moles of electrons to cancel, and 96,485 coulombs on top. So that way moles of electrons is gone. So if we stopped right now, our answer would be in coulombs. The problem told me that they're going to run a current that has 100 amps, and we know 100 amps is 100 coulombs per second. So 100 coulombs equals 1 second. I put 100 coulombs on bottom of the fraction, 1 second on top, so that way my coulombs cancel, and we're left with this giant number of seconds, 1.07 times 10 to the 5th seconds. So I'm just going to do some conversions to make it a little nicer. So here's my seconds. I just brought it down, 60 seconds in a minute. So seconds is gone. If we multiply there, it was still a big number, so I did 60 minutes in 1 hour. Minutes are gone, so now I got my answer in hours, something I can actually kind of conceptualize, 29.8 hours, so about 30 hours. So how long will it take? If I want 1,000 grams or 1 kilogram of aluminum to be made, it's going to take 30 hours with a current of 100 amps to make that. Here's another one that is similar to something you might see on your problem set. So electrolysis of an alkaline earth metal, chloride. So we have something, alkaline earth is in that second column on the periodic table, so it has a +2 charge. It's bonded with Cl-. Okay, we're going to use a current of 5 amperes for 248 seconds, and they're telling me, because we don't know what this alkaline earth metal is, they're telling me the grams of the metal. Okay, so we're going to have to work here to figure out what that metal is. So you can check your answer. Here's kind of what I figured out. Well, the alkaline earth metal has a +2 charge, so I'm just going to call it X. So X + 2 needs to gain 2 electrons to make this solid. Okay, and I know ultimately I'm trying to find from these unit conversions the moles of the metal. Because I have grams, they told me it's going to make 0.471 grams. So if I can find moles using my calculations, I know grams divided by moles is going to give me molar mass. So if I lost you in those calculations, here's a couple labels for you. So I started with the time on this one. So we're working in the same direction as those steps I gave you for that first problem we walked through. So I have 748 seconds. I know that the current is 5 amperes, so 5 amperes is equal to 5 coulombs per second. I split that apart, so I can put 5 coulombs on top, 1 second on the bottom, seconds cancel, now I'm in coulombs. I use Faraday's, so now we're going to divide by Faraday's constant, right? 96,485 coulombs is 1 mole, so that way my coulombs will cancel. If we stopped right now, we'd be in moles of electrons. But moles of electrons doesn't help me, I want moles of the metal. So I know that because it's an alkaline earth metal, it's going to take 2 moles of electrons for every 1 mole, because alkaline earth metals are in that second column on the periodic table, so they have a +2 charge. So that way moles of electrons are gone, and now we're in moles of X, whatever this X is. So I have moles of X. Molar mass is equal to grams divided by moles, and they told me I'm going to make 0.471 grams of the metal. So grams of X divided by moles of X, right? 0.471 grams divided by 0.0914 moles will give me the molar mass of 24.3 grams per mole of this metal that I'm producing. So what alkaline earth metal in that second column has a molar mass of around 24? It's magnesium. Alright, the last type of problem you might see is where you have to predict the products or predict what's forming at the anode and cathode, and there's 2 solutions. So if you just have the molten ionic compound, like the NaCl example, where you melt this ionic solid, no water, the cation is going to be reduction, the anion is going to be oxidized, and we figure that out from writing a little reaction. I'll show you one in a second. The tricky part is if it's a solution or aqueous and water is present, then we have to figure out basically we have a competition between the ions that might be reduced from the ionic compound and water. So we have to look at the E's reduction values to figure out. But here's some tricks as a rule that might work. So no 1A or 2A metals, so column 1, column 2 alkaline metals, alkaline earth metals, will be reduced in an aqueous solution. Water is going to be reduced instead. And no polyatomic ion will be oxidized. Water will be oxidized instead. So those are tricks, but I'll show you how to figure this out. All right, this is something we just kind of need to know. Like, these are going to be on your reduction potential chart, but you have to know that they're like important, if that makes sense. So you have to know that these are the main ones we're going to use. So if we have an aqueous solution with the ionic solid and water, we are going to compare the reduction potentials of the ionic compound with that of water. So for oxidation, we're going to compare this reaction. 2H2O produces O2 plus 4H plus 4 electrons, and that has a reduction potential of 1.23 volts, and we're going to compare the negative version, the oxidation one, with whatever's being oxidized in the ionic compound. So why is this the oxidation one? Well, if you look, here's my water, but oxygen goes from -2 to 0. So in this case, oxygen, so to speak, is oxidized, but because it's a part of water, we're calling it the oxidation of water. For reduction, we're going to take 2 waters plus 2 electrons, makes H2 plus 2 OH minuses. If you look in this, our H plus goes from a +1 oxidation state to 0, so it's gaining electrons. So even though it's part of water, we're saying that water is being reduced. Okay, so how do I figure out when I'm comparing? Well, at the cathode, we're looking for the higher reduction value. At the anode, we're looking for the more positive or higher oxidation value. So here's a typical problem. You actually have to do this one, I think, on your problem set. What reactions will take place at the cathode and the anode when each of these is electrolyzed? So here's letter C. We have molten, so no water present, MnI2. So your first step with these is you take that ionic compound, MnI2, and you break it into the ions, your elements, I should say, no ions, excuse me. Mn, and then iodine is one of the Hike-Bro-Need Cliff bars, the diatomics. So it's the I in the word cliff, so that gets a little 2. Either way, we can assign oxidation numbers, +2, -1, 0, 0. We can see what's reduced, what's oxidized. So we know oxidation happens at the anode, so that's the I. So we write then the oxidation for, we write the oxidation reaction for I2. So 2I minus goes to I2 plus 2 electrons. Here's the reduction potential. I turn it negative for oxidation. Cool, that doesn't really make a difference for us right now, but it will on the next slide. Okay, then we do reduction. So the manganese 2 plus 2 electrons makes solid manganese, and we have our reduction potential. So in this particular reaction, because we don't have water, I know what reactions are taking place at the anode and cathode. Super easy. I know what products are being made, I2, manganese, if they ask for products instead of the half reactions. This one, what reaction takes place at the cathode and anode when each is electrolyzed, and this says solution. So that word solution tells me that there is water present. So we have to compare what we just looked at on the last slide with the reduction potentials of water. Alright, so this part is exactly the same from the last slide. I copied and pasted. Same with this. Exactly the same. Exactly the same. But notice I said possible reductions, possible oxidations. So what I did here now is we have the oxidation reaction, half reaction for water. Notice oxygen is going from a -2 oxidation state to a 0 oxidation state. Here's the reduction value. I turned it negative to show that it's oxidation. And I'm comparing these oxidation values. Who's more positive? The I minus half reaction. So I minus will be oxidized at the anode. I2 will be produced at the anode. Now we do the same for reductions. Mn2 plus 2 electrons makes Mn. Great, we had that last slide. Here's the reduction half reaction for water. Water H goes from +1 to 0, and we have the reduction value. We look what's more positive. In this case, the water half reaction is more positive. It's a bigger number, so water will be reduced at the cathode. What would form at the cathode? If they ask that follow-up question, we would have hydroxide, and we have hydrogen gas. H2 is a gas at room temperature. Okay, so that's how we solve these problems.